Massive stone blocks were shaped and placed with impossible precision. Ancient cultures across the world built monuments from granite, a rock so hard it defies modern steel. Yet with what we assume were simple copper tools and sheer manpower, they created structures that have lasted for millennia. There is a profound disconnect here, a gap between the technology we think they had and the staggering achievements we can still see today. This video will dissect the specific engineering puzzles that leave experts baffled, from moving 1,000-ton stone to cutting it with flawless seams. By the end, you will understand the constellation of sophisticated techniques, some possibly lost to time, that made these wonders possible. How did they quarry a single block taller than a 5-story building? What method allowed them to fit stones so tightly a razor blade cannot slip between? The answers are more complex and more human than any single secret. What does it truly mean for a work of stone to defy time? Granite was not an accidental choice, but a deliberate declaration. Across continents and centuries, ancient builders consistently reached for the most stubborn, unforgiving stone on Earth. This was not a matter of convenience, for granite is notoriously difficult to work. Its extreme hardness comes from a dense interlocking crystal structure of quartz and feldspar, a geological armor that laughs at ordinary tools. Such a monumental struggle, the answer lies in a profound understanding of material and meaning. Granite possesses a compressive strength that is almost unbelievable, allowing it to bear colossal weight for millennia without crumbling. It is virtually impervious to weathering, resisting wind, rain, and temperature swings that would reduce softer sandstones to dust. When you built in granite, you were building for eternity. You were creating a legacy meant to outlast kingdoms, languages, and even memory itself. The symbolic permanence was as crucial as the physical. In Egypt, towering obelisks like the unfinished specimen at Aswan, which would have weighed over 1,000 tons, were carved from a single piece of red granite to pierce the sky and connect the pharaoh to the sun god. In the Andes, the Inca shaped andesite and granite blocks at sites like Sacsayhuamán into polygonal puzzles, walls that have withstood devastating earthquakes because the stone itself refuses to break. Even the bluestones of Stonehenge, though not granite, represent a similar testament to extreme effort, transported over hundreds of miles from their source because their specific material properties, perhaps their durability or symbolic significance, were deemed non-negotiable. This global pattern reveals a shared imperative, a universal engineering philosophy. These cultures were not avoiding the easy path. They were deliberately choosing the hardest one because the material itself was the message. The very difficulty of granite guaranteed its legacy, so the real puzzle begins not with how they moved the stone, but with understanding the sheer will required to look at a mountain of granite and decide to make it into a monument. The first and greatest challenge was always extraction, the act of convincing a continent to give up a piece of itself. But separating a monument from a mountain is a problem of physics on a brutal scale. The initial quarrying of these multi-hundred-ton blocks stands as the first impossible task. We know some of their tools, simple yet effective. In Egypt, workers are believed to have used balls of dolerite, a stone even harder than granite, to pound along a desired line for days or weeks, pulverizing the rock grain by grain into a shallow trench. Elsewhere, the technique of drilling a line of holes, inserting dry wooden wedges, and then soaking them with water was employed. The wedges would swell with tremendous force, creating a clean fracture along the predetermined line. These methods work, they are proven, but when you scale them up to the dimensions of the Aswan obelisk or the colossal foundation stones at Baalbek, the numbers become staggering. The labor investment shifts from impressive to almost incomprehensible, coordinating hundreds of workers to swing stone hammers in unison for months, managing food, water, and shelter at a remote quarry site, all to free a single block that still had to be moved. This speaks of a society capable of staggering logistical coordination and long-term vision. It forces us to ask a deeper question. Were these pounding and wedging techniques the full story, or were they merely the final, visible steps in a more sophisticated process we have missed? Some researchers point to the remarkably flat, sheer surfaces left on quarry walls and wonder if a method for initiating deep, controlled fractures has been lost. Could fire have been used strategically to thermally shock the granite, creating weaknesses for tools to exploit? The sheer efficiency implied by some ancient quarries, where blocks seem to have been popped free with almost surgical precision, suggests we may still be underestimating their initial mastery of the stone. The quarry floor was their first workshop, and the evidence there hints that their engineering genius began long before the block ever budged. The clearest window into this ancient struggle is not a finished monument, but a spectacular failure. In the granite quarries of Aswan, Egypt, lies the Unfinished Obelisk, a colossal shaft still attached to the bedrock. It is a snapshot of quarrying frozen in time, a project abandoned over 3,000 years ago. If completed, it would have been the largest single piece of stone ever carved by human hands, standing over 100 feet tall and weighing an estimated 1,200 tons. Its value to us today is immeasurable, for it shows the process in raw, incomplete detail. We can see the deep trench, roughly 3 feet wide, that workers carved around its outline by relentlessly pounding with dolerite balls. The sides of this trench are remarkably straight and vertical, a testament to the controlled, grueling effort of hundreds of laborers working in a confined space for many months. This presents its own logistical puzzle. How did they manage the removal of the crushed granite debris from such a deep, narrow channel? How did they coordinate the swing of so many hammers without shattering each other's tools or limbs? The workspace itself was an engineering challenge, yet the most telling clue is the reason the obelisk was abandoned. A large, pre-existing crack was discovered running through the granite as the work progressed. This flaw made the stone structurally unsound for its intended purpose. This failure is profoundly instructive. It shows that even with their immense skill, the ancient Egyptians were not infallible. They were subject to the same material constraints we face today. It raises a critical question about their knowledge. Did they have a method for assessing the internal integrity of the bedrock before committing years of labor? Or was this a tragic, costly lesson learned through experience? The Unfinished Obelisk is not a testament to what they could not do, but a rare and honest record of the immense risk they undertook every time they set out to conquer a mountain. It makes their successes elsewhere with flawless stones seem even more remarkable. The block was now free, but its journey had only just begun. The sheer scale of the labor involved in traditional pounding and wedging forces a difficult question. Could there have been a smarter, less brutal starting point? This is where we enter the realm of alternative hypotheses, where scientists and historians look for methods that could have dramatically reduced the initial effort. One compelling idea centers on thermal shock, a process known as fire setting. The concept is straightforward but clever. Build a hot fire directly against the granite face you want to quarry. The intense heat causes the surface layer of the rock to expand rapidly. Then douse the heated stone with water, often cold water from a nearby source. The sudden, violent contraction from the cooling creates immense internal stress. This thermal shock can cause the granite to fracture and spall, flaking off in layers or cracking along crystal boundaries. It effectively pre-weakens the stone, making the subsequent work of pounding or wedging far more efficient. There is strong archaeological evidence for fire setting in metal mining across the ancient world, and its application to granite quarrying is entirely plausible from a materials science perspective. The real debate is about the scale and control. Could ancient workers have managed fires large and hot enough to affect the deep, massive blocks needed for monuments? And could they have directed the fracturing with enough precision to avoid ruining the stone? While no definitive proof like soot stains has been found on every quarry face, the idea remains a strong candidate for a lost efficiency technique, a way to turn months of pounding into weeks. Another, more subtle hypothesis involves chemistry rather than brute force. Granite, while immensely hard, is not a uniform substance. Its crystals of quartz and feldspar are bound together by interstitial minerals. Some researchers have proposed that ancient masons might have used acidic organic compounds like sour wine or vinegar, or even plant saps with corrosive properties. Applied to a pre-drilled line or a natural fissure, these weak acids could very slowly dissolve the mineral glue between the crystals. Over time, this would create a natural fault line, a zone of weakness that would make splitting the block much easier. The evidence here is more circumstantial. We know many ancient cultures had fermented liquids and knowledge of basic plant chemistry. The concept is scientifically sound, as even mild acids can weather granite over long periods. However, demonstrating that this was an intentional, controlled quarrying technique rather than a natural weathering process is incredibly challenging for archaeologists. It leaves little trace beyond the finished product itself. Both of these hypotheses, thermal shock and chemical weakening, address the core paradox. They are attempts to solve the time and effort equation, to find the clever shortcut that explains how human hands could begin to master a mountain. They may not be the definitive answer, but they expand our view of ancient innovation beyond the swing of a hammer. They suggest a toolkit that was both physical and intellectual, employing observation of natural processes and a deep, experimental understanding of the material itself. If the block could be persuaded to help in its own liberation, the real miracle of movement might just become possible. Freeing the stone was only the beginning of its transformation. Now came a challenge of pure physics and human coordination, moving an object the weight of a small warship across a landscape that offered no cooperation. A 1,000-ton block of granite does not simply slide into place. The friction between such a mass and the ground is astronomical, a force that would grind any ordinary sledge to splinters or bury wooden rollers into the soil like nails. To move the immovable, ancient engineers had to fundamentally change the rules of the game, and their primary strategy was elegant in its simplicity: reduce the friction at all costs. The most iconic image is the wooden sledge, a massive timber platform upon which the stone block was secured. But a sledge alone is useless. Its runners would instantly seize against the earth. The solution was a lubricated pathway. Egyptian tomb paintings and archaeological evidence point to the use of liquid, likely water or a slurry of wet clay, poured ahead of the sledge's path. This created a slick, muddy surface that dramatically lowered the coefficient of friction. Think of it not as dragging a stone, but as sliding a colossal ice cube across a wet floor. The physics are sound, and experiments have shown that with enough workers pulling on ropes, even enormous weights can be shifted this way. Yet the practical execution on the scale of a megalithic block introduces staggering logistical puzzles. How was the water supply managed across a desert route? How were the ropes, which must have been as thick as a man's thigh, manufactured and kept from snapping? And this method implies a prepared road, a causeway of packed earth or stone that was leveled and reinforced to bear the concentrated load without collapsing. At the Lebanese site of Baalbek, home to the largest known cut stones on Earth, the so-called trilithon blocks, each weighing around 800 tons, were moved nearly a mile from their quarry. The path they took, still visible today, is a constructed roadway of fitted stone, an engineering project in its own right built solely to serve the movement of these giants. This reveals a critical layer of the endeavor, the infrastructure behind the spectacle. Moving a megablock was not a single heroic effort. It was a campaign that required road builders, water carriers, rope makers, and coordinators working in a precise, synchronized sequence. The pull itself was a feat of social organization. Teams of laborers, sometimes numbering in the hundreds, would have needed to haul in perfect unison, guided by rhythmic calls or drumbeats to apply their force simultaneously. A single mistimed pull could cause the sledge to stick, wasting precious energy and risking the safety of everyone involved. This transforms the image from one of brute force to one of choreographed precision, a slow, deliberate dance where human muscle was amplified by clever physics and meticulous planning. But even with sledges and water, the strain on materials and men would have been at the very limit of endurance. This leads us to wonder if there was another piece to the puzzle, a forgotten method that made the impossible merely difficult. The most vivid evidence for this monumental haul comes not from a quarry but from a tomb. In a wall painting from the tomb of Jehutehotep, a nobleman from ancient Egypt's Middle Kingdom, we see a detailed scene of a colossal statue being transported. The statue, estimated to weigh around 60 tons, rests securely on a large wooden sledge. A team of 172 men pulls forward on 4 massive ropes, while a figure standing on the knees of the statue pours what appears to be a liquid from a vessel directly onto the ground in front of the sledge's runners. This ancient illustration is a direct blueprint, a 2,000-year-old manual for moving the immovable. It confirms the core components of the most widely accepted theory, the sledge on a lubricated track. Experimental archaeology has put this theory to the test with compelling results. Teams have demonstrated that by wetting the sand or clay in front of a replica sledge, the friction can be reduced by as much as 50%. The liquid acts not as a simple lubricant but creates a crucial capillary bridge, a layer of damp particles that prevents dry sand from piling up in front of the runner. Instead, the sledge glides over a constantly renewed, semi-fluid surface. This transforms the problem from one of dry friction to one of fluid dynamics, a far more manageable task. But the choice of lubricant is a critical engineering decision with major implications. Water is the simplest candidate, but it evaporates quickly under the desert sun, requiring a constant and enormous supply along the entire route. A clay slurry would last longer and provide a more consistent slick surface, but its thicker consistency would require more initial pulling force to overcome its viscosity. Some have proposed the use of animal fat, which would not evaporate and could offer excellent lubrication, but the sheer volume needed for a multi-mile journey would be staggering, representing a significant economic cost. Each substance presents a different logistical puzzle, a trade-off between resource availability, preparation effort, and pulling efficiency. And this leads directly to the next overwhelming variable, the pulling force itself. To move an 800-ton block on a lubricated track, calculations suggest a required force equivalent to the combined effort of hundreds of strong individuals. The tomb painting shows coordinated teams, and this coordination was the true key. A disorganized pull would see forces canceling each other out, wasting energy and straining the ropes. The operation would have required rhythmic chanting or drumbeats, a primal form of metronome, to ensure every ounce of muscle was applied in perfect unison. This human element, the social engineering of turning hundreds of individuals into a single, living machine, may have been as vital as the wooden sledge beneath the stone. Yet this elegant system pushes other materials to their absolute limits. The ropes themselves become a point of intense speculation. Ordinary plant fiber ropes would snap under such loads. They would have needed to be incredibly thick, perhaps woven from papyrus or palm fiber into cables as thick as a tree trunk, and kept constantly wet to maintain their flexibility and strength. The strain on the anchoring points on the sledge and on the wooden sledge's own structure would have been tremendous. Every component, from the ground preparation to the final heave, existed in a delicate balance. A single failed rope or a dry patch of track could halt the entire enterprise. The sledge and lubricant method is not a magical secret. It is a testament to systematic problem solving on a grand scale. It shows us that ancient engineers understood fundamental principles of physics and friction, and possessed the organizational genius to marshal both materials and people into a slow, deliberate, and earth-shaking victory. Wooden rollers present an appealingly simple mental image. The idea is straightforward. Place a series of logs beneath the stone block, and as it rolls forward, workers continuously move the rollers from the back to the front, creating an endless, rolling road. In theory, this method significantly reduces friction compared to dragging, potentially requiring fewer people to move the same immense weight. It is a solution that feels intuitively correct, one we have all seen in diagrams and popular depictions of ancient construction. Yet when engineers subject this idea to the brutal mathematics of megalithic weights, the elegant theory begins to splinter under the load. The primary failure point is the wood itself. A block weighing 800 tons does not rest evenly on a roller. It concentrates its phenomenal mass onto a tiny contact point, an area perhaps no larger than a few square inches. The pressure at that point is astronomical, far exceeding the compressive strength of any known timber. Under such an extreme point load, the wooden roller would not simply indent. It would likely explode into splinters or be crushed flat into the soil beneath it, becoming a break, not a bearing. To prevent this, the ground would need to be paved with a perfectly rigid, level track of stone or hardened earth, and the rollers themselves would need to be made of an impossibly dense wood, or used in such vast numbers that the weight distribution changed, introducing a new cascade of logistical problems. This leads to the second, often overlooked operational nightmare, the roller relay. For the block to move continuously, a team of workers would need to scramble in the confined, dangerous space behind the moving mass to retrieve the emerging rollers and then run them to the front to be placed back into position. With a block dozens of feet long, this process would need to happen every few seconds, a frantic, high-risk ballet performed under the shadow of a shifting mountain of stone. The coordination would need to be flawless, and any misstep or delay would bring the entire operation to a shuddering halt. The margin for error was virtually non-existent, and the danger to the workers immense. When we scale this process up from a diagram to the reality of moving the Baalbek stones, the practical challenges become overwhelming. Most telling, however, is the silence in the archaeological record. While we have paintings of sledges and remnants of prepared causeways, there is a distinct lack of definitive evidence for the use of rollers with the very largest stones. We do not find caches of uniformly crushed giant timber rollers at quarry sites or along known transport routes. If rollers were the standard method for these mega projects, the physical evidence of their destruction under such loads should be everywhere. Their absence speaks volumes. It suggests that for the truly monumental blocks, the sledge on a lubricated track, for all its own difficulties, presented a more controllable, less destructive, and ultimately more reliable solution. The roller controversy ultimately teaches us a vital lesson about ancient engineering. It forces us to move beyond simplistic assumptions. It shows that these builders were not just applying generic techniques. They were making sophisticated choices based on a deep, practical understanding of materials, mechanics, and risk management. They chose the method that, while still extraordinarily demanding, offered the greatest chance of success when failure meant the loss of years of labor and an unmovable monument. The block was now on the move, but the next challenge was one of direction. How do you steer a 1,000-ton ship on dry land? A flat, prepared road was one challenge, but the landscape rarely cooperates with straight lines. The true test of an ancient engineer's ingenuity came when the path was not horizontal but vertical. How do you coax a 1,000-ton block up the side of a pyramid or onto a temple platform? The most widely accepted answer lies in the humble yet monumental earthen ramp. These were not simple piles of dirt but colossal, engineered structures in their own right. Builders would construct a gently sloping embankment of compacted earth, rubble, and brick, sometimes reinforced with timber, leading directly to the rising wall of the monument. As the structure grew taller, the ramp was extended and heightened, wrapping around the building in a spiraling ascent. The logistics were staggering, requiring the movement of nearly as much ramp material as monument stone. But the principle was sound, converting an impossible vertical lift into a manageable, albeit long, inclined pull. The physics are clear. A shallow slope dramatically reduces the force needed to raise a weight. Yet, even with a lubricated sledge, pulling such a mass up even a 5-degree incline would push human and material limits. This is where an even more clever system may have come into play: the counterweight. Imagine the sledge on the ramp, but instead of teams pulling it from the front, consider a heavy weight, like a container filled with stone or sand, descending a parallel track on the opposite side of the ramp. The two masses would be connected by ropes running over a simple wooden pulley at the crest. As the counterweight fell, its gravitational force would help haul the sledge upward. This elegant system would not eliminate the need for manpower, but it would supplement it, turning the brutal work of lifting into a more controlled process of guiding and balancing. While direct archaeological proof for such counterweight systems in ancient Egypt is sparse, the concept is mechanically straightforward and would have been within their understanding of leverage and gravity. It represents a sophisticated next step beyond pure hauling, an early form of mechanical advantage applied to the largest possible scale. Once the block reached its destination on the plateau or temple mount, the ramp would be carefully dismantled, leaving the pristine stonework behind, as if the mountain had simply grown into a new shape. But for some journeys, the most efficient road was not made of earth, but of water. For civilizations blessed with great rivers like the Nile, water transport offered a revolutionary solution to the friction problem. Moving a 700-ton obelisk by barge seems, at first, even more perilous than dragging it. The engineering, however, is brilliantly counterintuitive. The key principle is buoyancy, which lifts the crushing weight of the stone from the shoulders of men and places it on the supportive embrace of the water. The challenge shifts from overcoming friction to managing stability. The barge built for such a task would have been a colossal vessel, likely constructed near the quarry itself. To load the obelisk, engineers may have first dug a canal channel right up to the stone, allowing the empty barge to float into a prepared dock. Using a system of levers, ropes, and controlled flooding of compartments within the barge, they could have carefully rolled or slid the stone onto the deck, submerging the vessel slightly to receive the load, then sealing it and pumping it out to achieve a stable, floating state. The journey itself would have been a masterclass in calm precision. Towed by teams of smaller boats or guided by bankside haulers, the barge would ride with the current, its immense cargo actually making it more stable in the water. Upon arrival at the temple site, the process would reverse, with the barge docked and the obelisk gently offloaded onto a waiting ramp system for its final, short journey to the base. This method was not without its own colossal risks. A sudden storm or a calculation error in buoyancy could mean disaster, yet it exemplifies the adaptive genius of these builders. They did not fight the environment with a single, rigid technique, they partnered with it. They used the river's own nature to solve the problem the desert had created. Whether climbing a man-made mountain of earth or floating on a purpose-built island of wood, the goal was the same: to make the impossible journey a matter of patient, intelligent procedure. The stone had finally arrived, but its true transformation was only beginning. The stone now rested at the building site, a colossal but crude mass. Its transformation from a rough quarried block into a precisely shaped architectural element is perhaps the most perplexing stage of all. Here, the narrative collides with a stark physical reality: the precision-shaping paradox. The initial reduction of the block, knocking off major protrusions and bringing it closer to its final form, required a kind of controlled brutality. Workers would have used heavy stone hammers, likely made of dolerite or another hard igneous rock, to batter the granite surface. This was not delicate work. It was a thunderous process of calculated destruction, removing bulk through sheer percussive force. Yet this method alone could never produce the flawless flat faces, perfect right angles, and subtle curves we see on finished monuments. At some point, the process had to shift from brute force to astonishing finesse, and this is where the mystery deepens. Primary metals available to these early builders were copper and its alloy, bronze. Against granite, these materials are almost hopelessly soft. A copper chisel would blunt after just a few strikes, its edge folding over against the unyielding quartz crystals. To shape an entire temple facade or a sarcophagus with such tools seems an exercise in futility, a lifetime of labor spent just sharpening and replacing chisels. So how did they achieve surfaces so flat they can act as optical mirrors, or joints so tight they exclude light? The answer must lie in a suite of sophisticated secondary techniques that turned the hardness of the granite against itself. One of the most compelling methods involves the use of abrasive technology. Instead of trying to cut the granite, they ground it. Imagine a worker using a handheld stone, perhaps a piece of harder sandstone or emery, and a slurry of water mixed with an even harder abrasive powder like crushed quartz sand. By rubbing this paste back and forth across the granite surface with a flat stone, they are essentially sanding it down, particle by microscopic particle. This process, while slow, is relentless and controllable. It can produce a perfectly flat plane because the abrasive slurry fills low spots, ensuring material is only removed from the high points. To create a precise right angle, a craftsman might employ a guide, a true flat stone reference surface. By repeatedly sliding the block or the abrasive tool against this guide, the desired 90-degree angle would gradually emerge through patient, iterative grinding. This explains the incredible flatness, but what about the subtle curves and intricate details found on some granite artifacts? Here, the technique might shift to drilling and sawing, but again with an abrasive assist. A hollow tube, perhaps made of copper, could be rotated back and forth with a bow drill. The cutting action would not come from the copper itself, but from the abrasive slurry fed into the hole. The tube would slowly wear its way down, grinding a circular groove and leaving a solid core in the center that could be snapped out. For sawing, a similar principle applies: a copper blade pulled back and forth, its teeth loaded with abrasive slurry, would gradually wear a straight, precise curve into the stone. This marriage of soft metal and hard abrasive represents a brilliant technological leap. It acknowledges the limitation of their metals and bypasses it entirely, using the granite's own crystalline cousins to tame it. The final polish, that breathtaking mirror-like finish seen on statues and sarcophagi, would be achieved with progressively finer abrasives, culminating in powders so fine they feel like silk. The result is a surface that seems to defy the material's nature, a hard, rugged stone rendered with a soft, liquid smoothness. This painstaking process transforms the paradox from a question of possibility into one of time and will. It suggests that the true secret ingredient was not a magical tool, but a cultural capacity for sustained, meticulous effort, where the value of perfection outweighed the staggering investment of hours. The block was now a precisely formed component, ready for its final and most visually impossible act, the seamless join. The final, breathtaking polish on a granite sarcophagus hides a quiet revolution in ancient engineering. This was not a victory of force over stone, but of patience over time, achieved through a simple yet profound principle, the Abrasive Revolution. Confronted with granite's defiant hardness, ancient craftsmen made a brilliant conceptual leap. They stopped trying to cut it and started grinding it down instead. Their secret weapon was something as common as dirt, sand, specifically quartz sand, a material harder than the copper in their tools but composed of the same mineral found in granite itself. By harnessing a harder substance to wear away the stone, they turned a fundamental weakness into their greatest strength. The processes they developed were variations on this single, elegant theme. For sawing massive blocks, they likely used flat copper blades, not as cutting edges but as carriers. The blade would be pulled back and forth in a groove while workers constantly fed a wet slurry of quartz sand and water into the cut. The copper was simply a sturdy backing that pressed the sharp, angular sand grains against the granite. With each stroke, those microscopic quartz crystals scratched away a tiny, almost invisible amount of stone. It was an agonizingly slow process, but it was also perfectly controllable and could produce cuts of incredible straightness and smoothness. The proof is etched in the stone itself. Surviving saw marks on ancient granite often show parallel striations, the unmistakable signature of an abrasive being dragged back and forth, not the jagged gouge of a toothed blade. For drilling, the technique was equally ingenious. They used tubular drills, hollow cylinders of copper mounted on a spindle. As the drill was rotated, perhaps by a bow, an abrasive slurry was poured into the hole. The tube did not cut, it ground, wearing a circular groove into the rock. As the drill penetrated deeper, it would leave behind a solid, cylindrical core of stone in the center, which could later be broken free. This method explains the remarkably clean, circular holes found in everything from stone vessels to the famous core samples from Egypt, which still show the precise spiral groove left by the abrasive-laden drill. For creating vast, flat surfaces or precise angles, the work was even more hands-on. Craftsmen would use a flat reference stone, a true surface, and a simple handheld rubbing stone. Between the two, they would apply the abrasive slurry and grind the granite block against the guide over and over. This repetitive, meditative act ensured that high spots were worn down first, gradually converging on a plane of near-perfect flatness. The water in the slurry served a crucial dual purpose. It kept the abrasive particles suspended and mobile, and it carried away the heat and the ground rock powder, preventing the tool from clogging and ensuring a consistent finish. This suite of techniques elegantly solves the hardness paradox, but it immediately creates a far more human one, the time and labor paradox. To shape a single massive obelisk or a temple's worth of facing stones using only abrasives and muscle power represents an investment of time that stretches modern comprehension. We are not talking about weeks or months, but potentially years of continuous, focused labor for a single element. This forces us to re-evaluate the very nature of these projects. They were not construction sites as we understand them, but perhaps more like sacred workshops, places where generations of skilled artisans dedicated their lives to a single, enduring vision. The Abrasive Revolution reveals that the true monument was not just the stone, but the immense cultural value placed on perfection, a societal willingness to trade countless hours of human life for an achievement meant to outlast time itself. The stone was now shaped, but its most famous trick, the seamless join, required a final, almost magical touch. The granite itself holds the most reliable testimony, etched not in language but in microscopic scars. To understand how these monuments were built, we must become detectives, examining the stone's surface for the forensic evidence left by ancient tools. These marks are a permanent record, a direct physical connection to the hands that shaped them thousands of years ago. Some of the most revealing clues come from the process of drilling. In Egypt, archaeologists have studied unfinished artifacts and the solid cores left behind from drilling holes. These cores often show perfect, concentric grooves spiraling down their length, like the threads on a screw. These are the unmistakable signatures of a tubular drill used with an abrasive slurry. The copper tube, rotating back and forth, pressed quartz sand against the granite, grinding away a tiny ring of stone with each pass. The spiral pattern tells us the drill was not powered continuously in one direction, but was likely turned with a bow, creating a rhythmic back and forth motion that slowly, relentlessly ate into the rock. The consistency of these grooves speaks of remarkable control and a standardized technique mastered across generations of craftsmen. Equally telling are the surfaces meant to join together. At Inca sites like Ollantaytambo or Sacsayhuamán, the mating faces of enormous granite blocks are not just flat, they are astonishingly congruent. When two blocks are placed together, their surfaces conform to each other with such precision that they interlock in 3 dimensions. The tool marks here are different. They show a consistent, overall flatness achieved through persistent grinding with large, flat stones and abrasive paste. There is no evidence of large chisel strikes that would create dips or ridges. Instead, the surfaces were worn down evenly, a testament to a patient, methodical process of rubbing stone against stone until perfection was achieved. This technique, while simple in concept, required an incredible eye for geometry and an unwavering commitment to the final fit. Perhaps the most puzzling evidence, however, is an absence. On many finished granite surfaces, especially on statues, sarcophagi, and the interior walls of sacred chambers, there are no visible tool marks at all. The stone presents a flawless, often mirror-polished face. This lack of evidence is itself a powerful clue. It tells us that the final stages of work involved advanced polishing methods that completely erased the earlier, coarser grinding marks. This was achieved with a progression of ever finer abrasives, moving from coarse sand to powders as fine as flour, applied with rubbing stones and cloths until the crystalline structure of the granite itself was burnished to a reflective shine. The complete eradication of all prior scars indicates a final aesthetic goal that valued a seamless, almost liquid appearance, a surface that seemed to transcend its rocky origin. These silent surfaces challenge us the most, for they represent the culmination of the craft, a point where the evidence of the struggle was deliberately and skillfully removed, leaving only the perfect, enigmatic result. The joints between these perfect stones, however, present a final and visually impossible puzzle. Across the ocean, a different civilization approached granite with a philosophy that seems to contradict everything we have seen. In the high Andes of Peru, the Inca built not with straight lines and right angles, but with a breathtaking chaos of stone. Their walls are composed of massive, irregularly shaped granite blocks, each with a unique, multifaceted profile, fitted together in a tight, interlocking jigsaw puzzle. This is polygonal masonry, and it presents an engineering enigma that stands in stark contrast to the flat, plain precision of Egypt. Here, there are no long, lubricated tracks for sledges, no evidence of abrasive saws. Instead, the genius lies in a process of profound adaptation, a stone-by-stone conversation between builder and mountain. The most famous example is at Sacsayhuamán, the fortress overlooking Cusco. Its zigzagging walls are made from blocks so enormous, some weighing over 100 tons, yet fitted with seams so precise you cannot slip a piece of paper between them. The shapes are wildly irregular, some with 12 or more sides, each one custom carved to match the negative space of its neighbors. This creates a structure of incredible strength, a wall that moves and breathes as one solid mass during the earthquakes that frequently shake the region. The puzzle is not how they moved the stones, though that too was a feat. but how they achieved such a perfect custom fit between such complex, irregular shapes. The prevailing theory is one of iterative trial and error, a process that feels almost artistic in its patience. A master mason would select a roughly shaped block and have it moved into proximity with the wall. Using a technique likely involving stone hammers and possibly abrasive sand, workers would then begin to shape the face of the new block that would make contact. They would not work from a detailed blueprint, but from a direct physical template, the wall itself. They would repeatedly test fit the block, noting the high spots where it made contact, then carefully chip and grind those areas away before trying again. This cycle of test, mark, and adjust would be repeated dozens, perhaps hundreds of times, until the block settled into its destined space with a satisfying, airtight fit. This method implies a radical approach to measurement, one based on direct physical feedback rather than abstract numbers. The measuring tool was the gap itself, and the goal was to eliminate it completely. Some researchers suggest they may have used a soft medium, like wet clay, to take an impression of the receiving face, creating a direct mold to guide the shaping. Others point to the possibility of simple wooden templates or guide strings, but the core of the process was undeniably hands-on and relational, each block shaped in dialogue with the ones already in place. This improvisational genius required a deep, intuitive understanding of geometry and stone behavior. It also demanded a social structure where time was subservient to perfection, where a team might spend weeks or months fitting a single stone. The result is a wall that is not just a barrier, but a testament to resilience, each irregular interlock distributing stress in countless directions, making the whole far stronger than the sum of its parts. The Inca did not conquer the granite with rigid plans, they danced with it, creating a union between human intention and the natural chaos of stone that has withstood centuries of tectonic violence. The seamless puzzle of an Inca wall demands a practical explanation. How could a team without modern surveying tools achieve such a perfect, three-dimensional fit between stones of such wild, irregular shapes? The most compelling theories involve not magic, but a profound understanding of material and a masterful use of simple technology. One elegant idea centers on the use of templates. Imagine a mason taking a soft, pliable substance like wet clay or even a sheet of lead and pressing it firmly against the already set stone in the wall. This would create a precise negative impression, a perfect mold of that complex, multifaceted surface. This mold could then be carried to the new block waiting to be shaped. Craftsmen would use this physical template to guide their work, carefully chipping and grinding the granite until the new block's face matched the mold's contours. It was a direct transfer of information from stone to stone, a tactile blueprint that required no written measurements, only skilled interpretation. This method turns an abstract geometric problem into a straightforward, hands-on task of replication. Yet fitting the block was only half the battle. The final marriage of stone to stone might have involved a dynamic process known as bedding in. In this scenario, the multi-ton block would be carefully raised and lowered again and again onto its waiting neighbor. Each time it settled, the high points where the two stones made contact would bear the immense weight, creating stress concentrations. Workers could then identify these contact points, carefully dust them with a colored powder or simply mark them, and then grind just those specific spots away before repeating the lift and lower cycle. Over many repetitions, the two surfaces would gradually wear each other into a state of perfect conformity, a slow grind that used the stone's own weight as the shaping force. This transforms the act of construction into a kind of geological process accelerated by human intention. It is a patient, iterative dance that results in a joint where the stress is distributed evenly across the entire surface, not concentrated on a few points, creating a bond of incredible strength. This leads to the final, brilliant insight often visible in Inca walls, the principle of intentional convexity. Look closely at many of the fitted faces, and you will notice they are not perfectly flat. They often bulge slightly outward in the center. This subtle curvature is not a mistake. It is a masterstroke of seismic engineering. In a perfectly flat joint, an earthquake shaking could cause the stones to slide horizontally against each other. But with a convex face fitting into a complementary concave space, any lateral movement forces the block upward against the immense force of gravity. The earthquake's energy is thus converted into lifting work, a task so difficult it effectively locks the stones in place. This slight swell in the stone acts as a natural seismic dampener, a built-in resilience that has allowed these walls to stand through centuries of tremors. Together, these theories, template transfer, iterative bedding, and intelligent convexity, reveal a construction philosophy that was deeply responsive. The Inca mason was not imposing a rigid design upon the mountain. He was engaging in a dialogue with it, using observation, repetition, and a genius for structural physics to persuade individual stones to become a single, unshakable whole. The final challenge, however, was one of pure geometry, moving beyond trial and error to a realm of mathematical precision that seems to predict the future. This remarkable precision inevitably leads to a tantalizing question. Could there have been a shortcut, a way to bypass the crushing weight and friction entirely? In popular imagination, this question often finds an answer in the realm of the fantastic. The idea of acoustic levitation or lost anti-gravity technology. The narrative is seductive, picturing priests chanting at a precise frequency, their voices causing massive stones to rise gently into the air as if weightless, or a mysterious device that simply cancels out gravity's pull. These stories speak to our desire for a clean, almost magical solution to such a dirty, difficult problem. They suggest a hidden chapter of history, a forgotten science so advanced it appears as magic to us today. While captivating, this hypothesis collides with the unyielding wall of established physical law. The principle of acoustic levitation is real, but only on a microscopic scale. Modern laboratories can use precisely tuned sound waves to suspend tiny particles or droplets in mid-air, a delicate balancing act of pressure nodes. Scaling this effect up to lift an object weighing hundreds of tons, however, requires energy levels that are not just impractical, they are catastrophically unimaginable. The sound pressure needed would be so intense it would not only shatter the stone but instantly incapacitate any living thing for miles around. It would be less a construction technique and more a weapon of unimaginable power. The anti-gravity concept is even more problematic, as it posits a technology that manipulates a fundamental force of the universe in a way that remains entirely theoretical, with no known mechanism even in our most advanced physics. More critically, there is a complete absence of evidence. No ancient text, no wall carving, no archaeological find describes or depicts such a device or ritual for moving megaliths. The detailed tomb paintings of Egypt show sledges, ropes, and men straining. They do not show floating stones. The practical builders left us a clear record of their immense labor, not a secret they forgot to mention. This matters because the levitation myth, while fun, can unintentionally diminish the genuine achievement. It suggests that the real work, the coordinated effort of thousands, the brilliant engineering of ramps and lubricants, the patient years of abrasive shaping, was somehow not enough, that it requires a supernatural explanation. In doing so, it steals credit from the cultures that accomplished these wonders with the tools, minds, and muscles they possessed. The grounded engineering explanations are not less impressive, they are more human. They show us societies capable of breathtaking organization, innovation, and perseverance. They reveal a truth far more compelling than any lost secret, that human ingenuity, when focused collectively on a single goal across generations, can achieve what later ages might mistake for magic. The stones did not float, they were persuaded, and that persuasion is the real story. The true marvel may not be a forgotten machine, but a living one. Behind every perfectly fitted stone lies an achievement of social engineering just as complex as the physical engineering, a symphony of human coordination played out over generations. To focus solely on lost technology is to miss the profound reality. These monuments were built by societies that mastered the art of mobilizing people on a scale that still stuns the modern mind. The quarry was not just a work site, it was the heart of a sprawling, temporary city. Thousands of laborers, not slaves in chains as often imagined, but likely skilled workers, farmers during the off-season, and conscripted citizens fulfilling a duty to the state, would descend upon a remote location. Their first task was not to cut stone, but to build the infrastructure to support the cutting. Vast camps sprang up with barracks, bakeries, breweries, and infirmaries. Archaeologists at Giza have uncovered the remains of such a workers' village, complete with evidence of large-scale food production, including bones from cattle shipped from across the kingdom. This reveals a supply chain of breathtaking scope, a constant river of grain, fish, pottery, tools, and fresh water flowing into the site to sustain the human engine at its core. The project management required to keep this system functioning for decades, even centuries, is a silent testament to administrative genius. Scribes would have maintained meticulous records, tracking work gangs, tool inventories, and ration distributions. Foremen, engineers, and priests formed a clear hierarchy, translating the pharaoh's or king's divine vision into daily, actionable tasks for the workforce. This was not chaotic toil, it was a meticulously scheduled and segmented operation. Different teams would have specialized in specific tasks, one group for initial quarrying, another for rough shaping, another for fine finishing and transport. Their work was phased, with quarrying operations planned years in advance to ensure a steady supply of blocks matched to the construction schedule rising miles away. The rhythm of life was dictated by the project's needs, with work possibly organized into shifts and marked by seasonal pauses. This level of organization transforms our understanding of the labor. It was not mere brute force, but force intelligently directed and sustainably supported. The true technique was this invisible framework of logistics, command, and care. It was the ability to align the wills and muscles of thousands toward a single, long-term goal, maintaining morale and purpose across lifetimes. The monument, in the end, is as much a memorial to this collective human endeavor as it is to the ruler it honors. It stands as proof that when a society organizes itself with enough clarity and commitment, it can achieve works that seem to defy the very limits of its time. Yet the most powerful tool for unraveling these mysteries isn't found in a textbook, but in the dust and strain of a modern experiment. Experiential archaeology, the practice of learning by doing, has brought these ancient puzzles into the sharp light of physical reality. Teams of researchers and dedicated volunteers have rolled up their sleeves to test these theories with their own hands, trading speculation for sweat and blisters. One of the most comprehensive efforts was led by archaeologist Mark Lehner and a team in Giza. They set out to build a small pyramid using only the tools and techniques believed available in the Old Kingdom. The project was a profound lesson in humility and insight. They successfully quarried limestone blocks using simple copper chisels and stone pounders, confirming the basic feasibility. They moved blocks on wooden sledges along a lubricated path of wet clay, demonstrating that a small team could indeed shift multi-ton stones. But the experiments also revealed hidden complexities the ancient texts never mention. The copper chisels dulled astonishingly fast, requiring constant resharpening by a dedicated team of workers, a logistical detail easily overlooked. The wet clay track required meticulous maintenance to prevent drying and cracking. Most tellingly, the sheer, grinding pace of the work under the Egyptian sun gave the researchers a visceral understanding of the project's human scale. It was not just about moving stone, but about managing endurance, preventing injury, and maintaining morale over a timeline that stretched for decades. This experiential approach strips away romantic notions and replaces them with a gritty, practical truth. Another famous experiment took place in the 1990s when a Japanese television consortium teamed with Egyptian archaeologists to erect a small obelisk. Their goal was to test a complete sequence from quarrying to raising using only ancient methods. They succeeded in carving a 35-ton granite obelisk using dolerite pounders, a process that took months. They transported it on a giant sledge pulled by dozens of workers on a lubricated track. But the final act, raising the obelisk from horizontal to vertical, presented the greatest danger. Using a simple earthen ramp and a pivot point at the base, they carefully inched the stone upward. The moment of truth was tense as the obelisk's immense weight threatened to snap ropes or slip from its pivot. When it finally settled into its base, the success was triumphant, but the margin for error was terrifyingly thin. These experiments teach us two crucial things. First, they confirm that the proposed techniques are fundamentally sound. They work within the laws of physics. Second, and more importantly, they illuminate the immense skill, risk, and time investment that these methods entailed. A failure in any one step, a snapped rope, a dried track, a misaligned pivot, could mean disaster, wasting years of labor. This transforms our view of ancient engineers from mystical figures into brilliant, practical project managers who understood materials, mechanics, and human limits with an intimacy we can only approximate. Their genius lay not in defying physics, but in mastering its every demanding detail through hard-won experience. But the true purpose of these stones often extended far beyond the physical. For many ancient builders, the engineering challenge was not merely to place a stone, but to place it in precise conversation with the heavens. This introduces a secondary, breathtaking layer of complexity, the mathematical and astronomical alignment of granite monuments. Imagine the task: not only must you move a 1,000-ton block, but you must position it so that on one specific morning each year, a sliver of sunlight pierces a narrow corridor to illuminate a sacred chamber, or so that its shadow falls exactly along a predetermined line at the summer solstice. This requirement transforms construction into a form of celestial surveying, demanding a deep integration of astronomy, geometry, and long-term planning into the already immense physical labor. The Great Pyramid of Giza, though built of limestone, provides the most famous example of this principle. Its sides are aligned to the cardinal directions with an accuracy of better than 1/15th of a degree, a feat that would have required sophisticated observational techniques using the stars. But granite monuments too were often designed as astronomical instruments. At the Inca site of Machu Picchu, structures like the Intihuatana stone, a carved granite pillar, served as a precise solar clock. Its angles and facets are positioned so that the sun casts distinct shadows at the equinoxes and solstices, marking the agricultural and ceremonial calendar. To achieve this, the stone had to be shaped, oriented, and set with incredible care, its functional purpose inseparable from its physical form. This alignment imperative forced engineers to become master planners. The entire site layout, sometimes planned decades in advance of the final stone being set, had to account for these celestial relationships. Surveyors would have used simple but effective tools, like gnomons to track shadows or aligned sighting poles to establish true north, performing their meticulous work over many seasons to gather the necessary data. This long-term observational data then had to be translated into the permanent, immovable language of architecture, etched into the landscape with multi-ton granite blocks. A slight error in calculation or placement, even by a fraction of a degree, would render the alignment useless after centuries of effort. This fusion of brute force engineering with delicate celestial precision suggests a society where knowledge was not compartmentalized. The same culture that could orchestrate the movement of mountains could also track the subtle dance of stars, seeing both as part of a single, ordered cosmos. The monument was not just a building, it was a clock, a calendar, and a statement written in stone and shadow, declaring that human order could mirror the eternal order of the sky. The scale of these projects forces us to confront a timeline that defies individual human ambition. A single pyramid or temple complex did not represent the work of one lifetime, but of many, a chain of effort stretching across a century or more. This multi-generational paradox presents its own set of profound questions. How do you maintain a consistent standard of precision when the master mason who laid the first cornerstone will be a memory by the time the capstone is set? The transmission of knowledge was the invisible scaffold holding the entire endeavor together. In a world without detailed architectural blueprints or engineering schematics, the plans lived in the minds and practices of the craftsmen, passed down through a rigorous system of apprenticeship. A young boy would enter a workshop, learning first to mix the abrasive slurry, then to pull the saw, then to shape a simple block under the watchful eye of his father or master. The techniques, the exact angles for a pyramid slope, the method for dressing a joint, these were not written down. They were muscle memory and oral tradition, ingrained through years of repetitive practice. This created a living library of skills where each generation inherited not just a task, but a sacred responsibility to uphold the vision. The project plan itself was likely encoded in simpler, more durable forms. A full-scale outline might have been laid out on a leveled desert floor with stakes and string, a giant diagram visible to all. Master models, perhaps small clay or stone mock-ups, could have been kept in a temple to serve as a three-dimensional reference for the high priests and overseers. The true blueprint, however, was the growing structure itself. Each completed course of stone set the unchangeable template for the next, a physical progression that locked in the geometry and left no room for reinterpretation. This required a society of astonishing stability. A king might order the work to begin, but his grandson would see only the foundation completed. The project had to outlive dynastic squabbles, economic fluctuations, and shifts in religious fervor. It demanded a cultural consensus so strong that the completion of the monument became a national identity, a shared purpose more powerful than any single ruler. To invest the labor of thousands for a goal none would live to see finished was the ultimate act of faith in the future. It framed these monuments not as vanity projects, but as civilization's bedrock, a literal and symbolic investment in eternity that declared, "We are not just building for today, we are building for a time when our names are forgotten, but our work will still teach." This long-term vision may be the most alien and impressive technique of all, one that modern society, with its short cycles and immediate returns, struggles to fully comprehend. This long-term vision challenges not only our view of society, but sometimes the very nature of the stone itself. A persistent and controversial idea whispers from the edges of mainstream archaeology, proposing that the builder's greatest secret was not how they moved the stone, but that they made it. This is the theory of geopolymer, a type of ancient man-made stone. Proponents point to certain enigmatic features as evidence: a puzzling lack of tool marks on some surfaces, stones that appear to flow around other objects, or the logistical nightmare of quarrying and moving every single block for a massive complex. They argue that what if ancient civilizations had discovered a form of advanced chemistry, a recipe to create a synthetic granite or limestone from a slurry of crushed rock, lime, and natural binders, then cast it into forms on site like an ancient monumental concrete. This would elegantly solve multiple problems at once, eliminating the need to move multi-ton blocks over vast distances and allowing for the creation of perfectly fitted, seamless shapes that would be nearly impossible to carve from solid rock. The known use of sophisticated lime mortars and plasters in the ancient world, like the Roman concrete that hardened underwater, is offered as a parallel, showing that advanced material science was within their reach. It suggests a lost branch of practical chemistry, a knowledge of geopolymerization that could turn a bag of powder into a mountain. The arguments against this theory, however, are grounded in the stone itself. Geologists who have examined the core samples from the Great Pyramid, for instance, find clear evidence of a natural sedimentary stone with intact fossil shells and the characteristic layering or bedding planes of limestone deposited in an ancient sea. These are features that could not be replicated by a cast material. The microscopic structure of the granite in Egyptian obelisks or Inca walls shows the interlocking crystalline pattern of rock that cooled and solidified under immense pressure over millions of years, not the more uniform, bubble-prone matrix of a poured composite. Furthermore, if such a versatile and revolutionary technology existed, why is there no evidence of its use in smaller, everyday objects? Why would a civilization with the power to make stone from dust bother with the backbreaking work of quarrying at all for any project? The mainstream scientific consensus remains firm. The megaliths we marvel at are indeed quarried stone, shaped by the immense physical and intellectual effort we have been exploring. Yet the geopolymer theory, while fringe, serves a valuable purpose. It is a testament to the sheer scale of the achievement, a measure of how extraordinary these monuments are that some feel compelled to invent a lost super-science to explain them. It highlights that the true mystery may not be in a forgotten chemical formula, but in the stunning culmination of all the techniques we have discussed, working in concert across generations. The stones are real, and that makes the human story behind them all the more incredible. But a monument story does not end the moment the final stone is set. The true test of an engineering philosophy reveals itself over centuries in how a culture cares for what it has built. The maintenance and repair of these granite giants is a quiet, overlooked chapter that speaks volumes about their creators' long-term thinking. These were not static artifacts, but living parts of a community that required stewardship. A crack appearing in a vital load-bearing block, the slow creep of plant roots into a joint, or damage from a rare seismic event. These were not signs of failure, but new problems demanding solutions. The very fact that many of these structures stand today, not as untouched ruins but as functional spaces used for generations, implies an ongoing, sophisticated understanding of the material. This was a knowledge passed down, a retention of the original lifting and shaping skills long after the glory of the initial construction had faded into legend. In Egypt, we see evidence of this in the great temples at Karnak. Over the reigns of dozens of pharaohs spanning 2,000 years, sections were expanded, renovated, and repaired. When a colossal granite column showed signs of stress, engineers didn't simply abandon it. They developed methods for stabilization, sometimes adding supportive masonry or even carefully dismantling and resetting sections using the same principles of leverage and ramp technology that built them. This was not a lost art but a living tradition. The Inca, masters of seismic resilience, also practiced a form of dynamic maintenance. After a major earthquake, teams would assess the polygonal walls. The genius of their construction often meant that blocks could settle back into place, but if one was shattered, a new stone had to be quarried and shaped to fit the existing, irregular puzzle. This required craftsmen who still understood the exacting process of trial, fitting, and bedding in, generations after the fortress was first raised. This continuity of skill suggests these societies viewed their monumental works not as completed projects, but as eternal responsibilities. The knowledge of how to move and shape granite was preserved within guilds or families, a sacred trust as important as the stone itself. It reveals a mindset where engineering was a covenant with the future, an acknowledgement that even the mightiest work of human hands is a conversation with time, requiring not just a brilliant first word, but a sustained and careful dialogue across the ages. Granite's extreme hardness places it in a category of its own, but to fully grasp the scale of its challenge, we must see it alongside its peers. The ancient world built with many stones, each demanding a different conversation between builder and material. Limestone, the primary block of the Great Pyramid, is sedimentary, softer, and more brittle. It could be quarried with copper chisels and wooden wedges with relative efficiency, its surface readily accepting detailed carved reliefs. Sandstone, used across India and the Middle East, is even more workable, its granular structure allowing for intricate sculptural forms. Working these stones was still a monumental task, but it existed on a different curve of effort. The shift to granite represents a leap not just in degree but in kind. Every technique had to be rethought, intensified, and fortified. Where a copper chisel could bite into limestone, it would only crumple against granite's quartz crystals. This forced the Abrasive Revolution, the patient grinding with sand, a method far slower and more resource-intensive than direct carving. The difference is etched into the artifacts themselves. A limestone wall might show the clear, sharp grooves of chisel work, while a granite surface reveals the subtle, overall flatness of relentless grinding, a finish achieved through attrition rather than incision. The adaptation extended to moving these giants as well. A limestone block, while still incredibly heavy, could be moved on a standard wooden sledge with a crew of a certain size. But a granite block of identical dimensions presents a radically increased frictional challenge due to its density and the need for a perfectly prepared track to prevent the sledge from digging in. The lubricant, the ropes, the pulling teams, all had to be scaled up or refined to handle the greater loads and the relentless pressure that threatened to crush any weakness in the system. This comparative view reveals a critical insight. The choice of granite was a deliberate escalation. It was the selection of the hardest possible mode. A culture that mastered limestone construction had solved one set of puzzles, but a culture that committed to granite was announcing it would solve every puzzle at its most difficult setting. They were not just building, they were engineering at the very limit of their material world, choosing the path of greatest resistance to guarantee a legacy of ultimate permanence. The most profound mystery is not in the stones but in the silence that surrounds them. Why, across these ancient cultures, do we find so few explicit instructions, no detailed engineering manuals or step-by-step guides left behind? The monuments shout their existence, but the methods whisper, forcing us to reconstruct genius from fragments. One primary reason is that this knowledge was often tacit, embedded in muscle memory and practice, not theory. The master mason did not learn from a scroll. He learned by standing beside his father, feeling the correct angle of a hammer strike, mixing the abrasive slurry to the perfect consistency by sight and touch. This was craft knowledge passed down through guilds and family lineages over centuries. Writing it down would have been as impractical as trying to describe how to ride a bicycle using only words. The essence of the skill lived in the doing. It was a living library, and when that chain of apprenticeship was broken by invasion, social upheaval, or the simple fading of a tradition, the library burned without a single scroll turning to ash. In other contexts, the silence was deliberate, a form of protection. The specific techniques for moving and shaping sacred stone could be considered restricted knowledge, a sacred secret belonging to priestly castes or the ruling elite. To reveal the methods might dilute their power or prestige, or worse, allow rival kingdoms to replicate their divine achievements. The magic of the monument, its ability to inspire awe and reinforce social order, depended in part on the mystery of its creation. Writing it all down for common eyes would demystify the divine right of kings. So, the knowledge was guarded, shared only in initiation rites and under vows of secrecy, ensuring it remained a source of power as long as the civilization endured. There is also the stark possibility that they simply saw no need to record what everyone knew. From our modern, document-obsessed perspective, this is difficult to grasp. But in a stable, traditional society where monument building was a continuous, multi-generational project, the techniques were not historical curiosities, they were the daily reality of work. Recording the obvious would have seemed as unnecessary as writing a manual on how to breathe. The scribes wrote of kings, gods, and conquests, the eternal things. The gritty details of ramp angles and rope tension were the domain of the foreman and the work gang, the background hum of civilization, not its celebrated narrative. Finally, and most devastatingly, we must confront the silence left by collapse. The most sophisticated engineering systems depend not just on skilled individuals, but on the vast, invisible infrastructure of the state, the administrative networks that feed workers, coordinate quarries, and plan decades in advance. When that civilization experiences a profound rupture through environmental change, economic failure, or conflict, that supporting structure vanishes almost overnight. The specialized knowledge, now isolated and without purpose, fades within a generation. The builders who knew how to true a 500-ton block become farmers. Their sons never learn the craft, and the language of stone is forgotten. The techniques were not lost in a single cataclysmic event, but evaporated slowly in the quiet aftermath, as the social memory that sustained them dissolved. The stones remain, eternal students waiting for a teacher who never comes, their lessons encoded in a language we are still struggling to decipher. So how would a modern engineering team approach moving an 800-ton block of granite? The answer reveals a stark contrast in problem-solving paradigms. Our first instinct would be to eliminate the human variable, to replace muscle with machinery. We would call in a fleet of heavy-duty hydraulic jacks, capable of lifting the stone millimeter by millimeter with computer-controlled precision. We would slide custom-built steel skids underneath, not wooden sledges, and place it upon a self-propelled modular transporter, a vehicle with dozens of axles and hundreds of tires, each with independent suspension to navigate uneven ground. To cut and shape it, we would not use sand but diamond-tipped saws and drills, materials harder than the granite itself, spinning at high speeds to slice through the stone like butter. These are our technological cheat codes, our way of bending physics to our will with pure applied force and advanced materials. The entire operation would be managed with laser surveying, digital models, and radio communication, compressing a project of years into a matter of weeks or months. This approach is brilliant, efficient, and utterly dependent on an industrial ecosystem that simply did not exist 4,000 years ago, and that is precisely what makes the ancient methods so illuminating. Our modern solutions rely on external power, on creating tools that are fundamentally alien to the task, harder, stronger, and more powerful than the material they confront. The ancient paradigm was one of integration and persuasion. They did not have diamond, so they used the diamond dust naturally present in quartz sand. They did not have hydraulic power, so they used water's fluid properties to reduce friction. They did not have steel cables, so they engineered ropes and social coordination to distribute load. Their toolkit was an extension of their environment, not a rejection of it. The necessity of their ingenuity is laid bare by the sheer inadequacy of their basic materials, copper and wood, when faced with granite. That they succeeded not by overpowering the stone with superior hardness, but by outthinking it with leverage, abrasion, and patience, reframes their achievement. It was not a lesser form of engineering, but a different branch of the same tree, one that prioritized deep material understanding and sustainable human effort over mechanized force. This gap in paradigms asks us a humbling question. Have we, in mastering the world with our machines, lost a certain intimacy with its materials, the kind of intimate knowledge that allows you to convince a mountain to become a monument? This brings us to the final and perhaps most important revelation. The greatest secret behind these monuments is not a single lost tool or a forgotten chant. It is the system itself, The true engineering marvel was the seamless integration of every technique we have discussed, from quarrying to final polish, into a single, fluid process. Each step was not an isolated miracle, but a carefully calibrated link in a chain, each one dependent on and optimized for the others. The method for quarrying a block directly influenced how it would be shaped for transport. The transport system dictated the design of the roads and ramps. The final fitting technique was chosen based on the stone's properties and the structure's purpose. This was not a generic construction manual applied blindly across the world. It was a deeply adaptive system, uniquely tuned to the local granite, the landscape, the culture, and the specific vision of the monument. The Inca did not try to build Egyptian pyramids, and the Egyptians did not attempt Andean polygonal walls. Each culture developed its own expression of the system, a holistic philosophy of stone that encompassed logistics, physics, and art. The quarry master communicated with the transport foreman, who coordinated with the master mason fitting the final joint. This flow of practical knowledge, refined over generations of trial and error, created a living tradition of problem solving. The system evolved through accumulated experience, with each successful project teaching a lesson that improved the next. A better lubricant discovered for moving stones might allow for larger blocks to be quarried. A new method for achieving a perfect flat plane might enable more ambitious architectural designs. This was engineering as a cultural conversation, passed down through apprenticeships and practiced until it became second nature. The impossible became possible not through a sudden flash of genius, but through the slow, steady perfection of an entire way of thinking about stone. The monument is the proof of this system's success, a physical manifestation of generations of coordinated intelligence, patience, and will. It stands not because of one magical trick, but because an entire society learned, over centuries, how to make a mountain obey. The puzzle endures because it is a perfect storm of factors, each one amplifying the others. First, the sheer physical scale defies our everyday intuition. We struggle to visualize the effort needed to move 1,000 tons, a weight that belongs to ships and skyscrapers, not to ropes and human hands. This scale collides with the second factor, the material's defiant hardness. Granite is not just heavy, it is actively resistant, a material that should have stopped their progress cold with the tools we assume they had. The third layer is the precision they achieved in spite of that scale and hardness. They didn't just move mountains, they shaved them into optical flats and fitted them with seams thinner than a hair. This level of control seems to belong to a different era of technology entirely. Finally, the historical record offers whispers, not shouts. We have the finished product in stunning detail, but the workshop manuals are missing. This sparse evidence forces us to reconstruct genius from fragments, leaving room for interpretation, for wonder, and for debate. It is this specific combination, immense weight meeting unyielding stone, resulting in impossible precision, all shrouded in partial silence, that creates a mystery so compelling. The enduring question is not a sign of ancient ignorance, but a testament to their sophistication. If their methods were obvious, the monuments would be less impressive. The fact that we must work so hard to understand their work only validates the depth of their achievement. Their legacy is not just in the stone, but in the enduring conversation it sparks across centuries. These silent stones are a testament to a different kind of engineering, one that wove together profound practical skill, immense social coordination, and deep cultural purpose. The monument is not a single answer, but a symphony of solutions, each note played by thousands of hands across generations. We may never uncover every detail of their methods, the precise consistency of the lubricant or the exact chant that kept the pullers in rhythm. Yet the very act of investigation, of testing these ideas with our hands and minds, does something vital. It expands our respect for the human ingenuity of the past. It moves us from a place of mystified wonder to one of informed awe. So the next time you stand before one of these ancient granite wonders, whether in a photograph or in person, try to see beyond the silent facade. Look for the slight convex swell of an Inca stone, the ghost of a saw mark on an Egyptian obelisk, the long, flat plane of a fitted joint. See not just a wall or a statue, but the culmination of 1,000 intelligent choices, a mountain of patient effort, and a civilization's bold declaration to the future. They are not simple and they are not silent. They are speaking to us still in the enduring language of human achievement.